Good morning. Today in physics lab, physics 1 lab, our experiment is about uniform acceleration motion. The main objective of this experiment is to prove the presence of the acceleration, a positive acceleration, a uniform acceleration, which means a constant acceleration. This acceleration will come from a hanging mass. In the experiment, the apparatus that we will use, we have a track with frictionless track. So the friction is very small, or it will be eliminated from the calculation. We have a car. We have a frictionless pulley. Also we'll use a balance, a recording tape, and an oscillator. Here we have a transformer just to transform the voltage of electricity, and here we have an oscillator that will oscillate with a frequency of 50 Hertz, which means that a time period of 1/50 is 0.02 seconds. So each 0.02 seconds we will have a dot on the recording tape. For the experiment setup, we have to put or attach the recording tape on the car. The recording tape should be the same length as the frictionless track. So as a hanging mass, we have a 31 gram. As you can see, we have 3 slits. Each one is 10 gram, and the holder is 1 gram, so a total of 31 gram as a hanging mass. The cord should be connected to the car. And from the second side, we have to connect the recording tape. So here we have the cord with the hanging mass connected to the car, and from the second side we have the recording tape passing by the oscillator. So now I will take it to the maximum position. So we turn on the oscillator, and now I will try to release the car without initial force. So here we have the dots. 0 is the starting point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as you can see from the dots, at the beginning, the separation distance between consecutive dots is too small. Between 0 and 1 is about 1 millimeter. And however, between 10 and 11, it becomes close to 1 centimeter. So the separation distance becomes bigger as we go by the experiment. Since the acceleration is constant, we have a positive acceleration coming from the hanging mass, that 31 gram hanging mass. So this hanging mass creates a tension on the cord, and this tension is applied, the same tension is applied on the car. So due to the tension, to the constant tension, we have a constant acceleration by applying Newton's second law. So we will have a acceleration m2 divided by m1 plus m2, where m2 is the mass of the hanging mass and m1 is the mass of the car. So and since we have a constant acceleration, a is constant, so v will increase as function of time, and same the x, the position, will be bigger as function of time. X will be equal to half at squared, where v will be equal to a times t. So now what we have to do is to measure the distance between consecutive dots, and to find, using the positions x, we have to find the velocity at given points, and using the velocity we will find the acceleration. So by using the position, so as you can see on this figure, we have the position x of different point, xi, xi minus 1, xi plus 1. By using xi minus plus 1 minus xi minus 1, we can find vi, where vi is xi plus 1 minus xi minus 1 divided by ti plus 1 minus ti minus 1. Ti plus 1 minus ti minus 1 equal 2 times tau period, which is equal to 1 over 50 hertz, so 0.02 seconds. 2 times tau equals 0.04. So in order to find, for example, V10, we have to use x11 minus x9 divided by 2 tau. However, in order to find the acceleration, AI is equal to Vi plus 1 minus Vi minus 1 divided by 2 tau. In this table, we have an example. So we need to find x9, the position x9, the position x11, and the position x13. Using x11 and x9, we can find V10. And using x13 and x11, we can find V12. And V12 and V10 will give us A11. So by applying the equation, I plus 1 minus I minus 1. So in order to complete the experiment, we need to do this example and 4 other sets in order to find 5 in total, 5 different acceleration at different points. So here we have A11, we can find A15, for example, A20, A5. So we can choose the points that we need, we want. After finishing the table and finding the acceleration, the different accelerations, the acceleration should be constant, but we will not find a constant acceleration experimentally. In the experiment, we have various sources of error coming from the frequency of oscillation, which may vary between 48 and 52 hertz. The friction coming from the trajectory, and the resistance of air, the air resistance. So we have various sources of error, and that's why we will not find a exactly constant acceleration. But the acceptable acceleration will be all values, or all value of acceleration that are smaller than the theoretical acceleration. The theoretical acceleration, which is m2 divided by m1 plus m2, where m1 is the mass of the car and m2 is the hanging mass. In order to find the mass of the car, we will use the balance, and here we have the balance and the car. The car balance is the car mass is 83.6 gram. So 83.6 is the mass of the car, and if you want, we can find the mass of the exact mass of the hanging, which is 31 gram or 31.1. Yes, 31 gram. So 31 gram as a hanging mass, and 83.6 gram for the car. So now we can find the acceleration, the theoretical acceleration, and experimentally all acceleration below the theoretical acceleration. So for example, if we will have a theoretical acceleration of 2.5 meter per second squared, all value below 2.5 per meter per second squared are acceptable. All value higher than 2.5 are rejected. And we have to complete the experiment by plotting the graph of x function of time, v function of time, and a function of time. So by plotting the graph, we will find that x function of time, which is half at squared, plus v0t, and since v0 is equal to 0, so x is equal to half at squared. Half at squared will be a parabola. So here we have the shape of x versus t. This is the theoretical shape, to be clear. Experimentally, we will have a dots below and above the line, but what we must plot is a parabola. However, v function of time is equal to 8 times t, v equal 8 times t, so we will have a straight line. Same, the dots on the graph will be below and above the graph, so, but we must plot a straight line, and straight line because we have a constant acceleration, so a constant slope. And for the acceleration, since the acceleration is constant, or we have a uniform acceleration, the value, we put the dots function of time, a function of time. However, we plot the horizontal line at a average. So we have 5 values of a, 5 different values, or 5 closed value of a. What we plot as a horizontal line is a average, the average value of this 5 acceleration. So a function of time should be constant, and we plot the line on the average value. As a conclusion for this experiment, using a car and a frictionless trajectory, we find that we have almost a constant acceleration, but due to various sources of error, as air resistance, friction coming from the trajectory, or the frequency of the oscillator, we didn't find an exact constant acceleration. However, the acceleration are close together, and we can conclude that we have a constant acceleration and then a uniform acceleration motion. And since we have a uniform acceleration motion, by plotting the graph of v function of time and x function of time, we find that for v it's a straight line, increasing straight line. However, for the x function of time, we find a parabola, which is very similar to the theoretical shape. That's everything about this experiment, and we will see you later in the coming experiment, in the next experiment.